Very good morning to everyone. So my name is Sudarshan Rao Mudu, and today I'll be presenting my PSM2 project, Skin Guard, a skin cancer detection web application with consultation feature, which is being supervised by Dr. Noor Aziza Ali. Okay, let's move on to the second slide. So before I begin, here's a quick outline of what I'll cover. I'll start with the project background and motivation, then walk through the aim, objectives, and scope. After that, I'll summarize the literature review and methodology used, give an overview of the system requirements analysis and design, then move on into implementation and testing, and finally wrap up the conclusion. And let's move on to the next slide. Okay, let's start with the problem. Skin cancer, especially melanoma, can be fatal if left untreated. But if it is caught early, the survival rate can reach as high as 99%. So early detection generally saves life. The issue is that dermatologists aren't always easy to reach, especially for people in the rural areas. This causes delays in diagnosis, and by the time someone does get checked, the condition has been progressed. Because of that, a lot of people turn to Google or unreliable sources online to try self-diagnose a mole or lesion. This often leads to inaccurate conclusion and further delays for proper care. That's the gap Skin Guide is designed to fill in. An integrated web platform that combines AI based image analysis with real-time dermatologist appointment booking, so users get a both instant assessment and clear path to real consultation if needed. The aim of this project is to help people to detect the skin cancer early, give them accurate results, and protect them from misleading online information or unverified home remedies. To achieve that, I set three main objectives. First, to understand the user requirement specification. Second, to collect and use properly classified skin lesion images dataset covering six categories, which is melanotic nevi, benign keratosis, like a lesion, and basal cell carcinoma, extensive keratosis, vascular lesions, and dermatofibroma. And third is to design and develop the actual web application. In terms of scope, the system uses a six-class skin lesion dataset sourced from Kaggle. It delivers real-time AI classification results through the web app and recommend nearby hospitals to so users can follow up with an actual doctor. Okay. Okay, now let's look at the two existing solutions, Skin Vision and Skin Check, and compare them against what I propose of Skin Guard. Neither Skin Vision nor Skin Check offers a built-in dermatologist appointment feature. Skin Guard does. Skin Vision gives an instant risk levels and let users track scans over time. It does hold class 1 certification in the UE. Skin Check offers more basic result reporting with the limited progress tracking. Skin Guard aims to combine the detailed AI classification with the historical scan tracking through as an academic project. It is even medically certified. On the technology side, I reviewed the Vision Transformer or a VIT architecture, which is a state-of-art model for the image classification and forms the basics of the AI analysis. I also looked into the React for building the interface, PostgreSQL as a relational database, and a VS Code as a primary development for the primary development environment. For the system development methodology, I choose Agile Scrum. This let me manage development in short 2 or 4 week sprints, which gave flexibility as requirements evolved during the project and reduced risk by testing the system in a small manageable increments. The Scrum cycle has 4 phases. In sprint planning, I selected features from the product backlog to work on, prioritized by importance. During the sprints themselves, I designed, implemented, and tested system modules within that fixed time box. In the sprint review, I demonstrated the completed functionality and checked it against the requirements. And in sprint retrospective, I reflected on the feedback to refine the plan going into the next sprint. For the actual build, I used React for the front end, Fast API for the back end, and Postgre for the database, and a pre-trained vision transformer model for AI inference, GitHub for version control, Jira for task tracking, and Draw.io for the UML diagrams. Okay, moving into the requirement analysis and design, the system has three main actors. The patient uploads the lesson image, completes a system visit, views the AI results, and books appointment. Hospital or clinic staff review the incoming reports by urgency, confirm or reject appointment, and manage their facility profile. And the admin managers uses queries and overall system administration. Here's a small sample of functional requirements I documented as a use case. For example, uh, use C001 ID covers a patient login, authenticating with email and password, where UC004 covers the registering new patient account, and UC005 covers a managing health profile, including age, skin type, and also the family history. For system architecture, I follow the model view controller or MVC pattern. This separates the application into three layers, which keeps the code base maintainable. The interface can change without affecting the underlying logic, and it lets each layer be developed somewhat independently. The model layer covers the core data entities like user patient profile, analysis report, appointment, and hospital. The view layer is the React-based interface for the both patients and hospital staff. And the controller layer is the fast API backend that handles the business logic and AI interface. On the database side, the core entities are profiles which store all the registered users, patient data for age, skin type, and family history. Doctors for clinic credentials and specializations, medical reports for uploaded images and AI results, appointments for booking and scheduling, and audit logs which track activity for security and compliance purposes. Okay. For the implementation, React powers both patient and hospital staff interface. Fast API serves the backend REST API with the AI integration, and Postgres stores all the system's data. In total, I built 12 functional pages across the two main actors. On the patient side, includes the registration and login, the patient dashboard, image upload and capture, image validation with a not safe for work filter, and also for step system visit, the AI analyst results page, hospital search using Google Maps, appointment booking and report history on the hospital staff side. There's a staff dashboard, a report review, that again confirmation page, and profile management. Altogether, that's 16 functional models built following a modular separation of concerns and architecture. For the testing, I used three approaches. Black box testing covered 25 test cases, 38 inputs, output scenarios, and 50 error messages checks, all with a 100% pass rate. White box testing achieved code coverage of 94% at line level and 97% at the branch level, focusing on the risk classification logic, uh, authentication, and database queries. The most meaningful validation through came from the user acceptance testing. I tested the system in actual dermatology clinic with a practical dermatologist and two real patients, and also I did public testing with the Digitex technology exhibition. The key outcome, that clinical validation dermatologists confirmed that AI risk classification matched professional medical judgment. For both real patients, one benign mole was correctly classified as medium risk, and one concerning lesion correctly flagged as high risk. During testing, I also identified resolved two defects on around the uh, two defects, filter threshold boundaries, and another involving a conservative bias trigger in the melanoma classification logic. Going back to the three objectives I set at the beginning, all three were successfully achieved. Understanding the requirements was achieved through literature study, interviews with the public and with the dermatologist or a clinic doctor, and analysis of existing app, all documented in the SRS. Designing the system architecture was achieved through a completed SDD, covering the technical architecture, database structure, and UI design following the MVC pattern. And building verifying the functionality of was achieved through black box, white box, and user acceptance testing, which confirmed the system meets all its functional requirements. Looking ahead, there are a few areas I would like to improve. First, the AI model itself could be trained or more on more diverse as a dataset and parameters fine-tuned further for better accuracy. Second, I like to extend the skin guide into a native mobile app to make it more accessible. And third, I want to continue expanding the test coverage, keeping test cases up to date and adding more as the system evolves. Ultimately, once all phases of design, development, testing are fully complete, the application would need further validation before it's ready for the ready world clinic deployment. That concludes my presentation. Thank you for your time and attention. Thank you for your time and attention. Thank you.